All right, so the other day in class, what we had done was we had started these introductory Atwood machine problems. Essentially, these are force diagram sort of exercises that we can do, talking about various sorts of machines and how these forces can be exerted via strings and ropes across pulleys, essentially changing the direction of the systems, really giving us quite literally elevators. But the idea is that it's a quick application of Newton's laws. And so that's going to be something that I'm going to talk a little bit about, not only through the course of these notes, but throughout the course of the entire unit, really, is how Newton's first and primarily his second law really get applied to these sorts of problems where forces are exerted in different directions via different surfaces and different objects. So to go over what it is we need to discuss in terms of the things the state wants us to have for honors physics, we need to, in some capacity, cover these half Atwood machines and full Atwood machines. Now, we're going to do these first in the absence of friction. So like for this first example problem, letter A, I ask you to represent all the forces present inside the diagram. We're going to neglect friction. Yes, I'm aware someone in class had actually mentioned, let me get to my little drawing function. Someone had mentioned in class that friction technically could be a force that is being felt by this sliding mass. We would label that F with a subscript of a lowercase f, at least in my class. And that is absolutely true. That is 100% accurate. That is something that we would normally need to take into account and consider, but we're going to ignore friction for now. We'll come back, and specifically with the half Atwood machines, we'll add that detail. We'll add that wrinkle to the whole thing. But that force specifically, we can go ahead and neglect and ignore. And that being said, there are a couple of other forces that we definitely need to talk about. The first force, if we're answering letter A, talking about all the forces that are present, is actually already represented here with you with this hanging block. We could label the hanging block H. It's got a mass of, they use a lowercase m, really just to signify that it's smaller in mass than the sliding block. Not super relevant to the problem just yet, but the idea is that these two blocks are of different masses. One is hanging over the edge, and gravity is able to work on that one that's hanging over the edge. So when we want to talk about the force of gravity acting on this hanging block, the letter H, we are going to represent that with the capital letter F. Again, all of our forces in my class I represent with the capital letter F. This one's going to get the subscript of a G because this is our force of gravity. This is how gravity is influencing that mass. And we can quickly find that. If you forgot from your reading notes, it's mass multiplied by your acceleration due to gravity. Really, it's Newton's second law, F equals ma. We're just being very, very, very specific about that source of acceleration, right? This is specifically the acceleration due to gravity. That's how you're going to calculate your weight. Remember, force of gravity and weight are the same. Mass and weight are not the same thing. Those are two very different values, two very different quantities. So we have the force of gravity pulling down on this hanging block. What's preventing this hanging block from falling is a force of tension being supplied by the rope pulling up, which is why, even in the demos I had in class the other day, that hanging mass didn't continue falling towards the ground. It eventually got stopped. The textbook likes to label this with a capital letter T, but they also use that for period later on. I don't like that. So I'm going to label it with a capital letter F, telling me that this is going to be measured in newtons. It is a force, and this is the force applied by tension of the rope. And we'll come back to that here in a moment. There's another force present here on the other end of the rope. The textbook goes through quite a bit of detail about how these two forces along the rope are going to be the same, right? Tension along a rope is going to be equal the entire length of the rope. And considering in this particular class, we're assuming these ropes are massless and do not contribute to the mass of the total system, there's really not a whole lot more we need to worry about there. I'll get to that in a moment. There are two more forces that we should talk about just for the sake of diagramming these forces and having this conversation. The first force is going to be another force of gravity, right? Gravity is not only working on the hanging mass. Gravity works on anything that is present in the Earth's gravitational field, right? Anything that's present on Earth. So the sliding block, M, or sliding block S, will also have a weight. It will have a force of gravity associated with it. Why doesn't that sliding block fall through the table, or why doesn't the cart, as the demo in the front of the classroom went over, fall through the track? The cart doesn't fall through the track. The sliding block doesn't fall through the table because there is another force equal and opposite to that value. And this is probably the most lazily named force force that I can come up with, that I can think of. But this is going to be your normal force, right? The normal force is essentially, if you go back to chemistry, it's your electrons repelling each other. It's your intermolecular forces, London dispersion forces, hydrogen bonding, all those fun things that hold molecules together. So long as you're not able to supply enough force to break those intermolecular forces holding those molecules together, that strength that those intermolecular forces have is referred to as the normal force. And it's what prevents objects, masses, things from occupying the same space at the same time. They physically can't because they get in the way of each other. Those electrons repel. That's what we describe the normal force as. It's a force that keeps anything apart. So you try to push on the wall. It's what keeps your hand from going through the wall. If you're sitting in a chair right now listening to this video, it's what's preventing you from falling through the chair. And you can overcome these intermolecular forces, right? If you get 3 or 4 people piling on top of each other in those cheap plastic flimsy lawn chairs that you can pick up outside of Jewel Osco for like 20, 30 bucks a chair, those are not going to hold 3 to 4 people. You've applied more of a weight force, more of a force of gravity than the intermolecular forces in that cheap plastic can hold. The normal force cannot counteract that, and it snaps and breaks and you fall to the ground, and it's somewhat humorous. Point is here, though, these two forces are canceling each other out, which is why the sliding block doesn't fall through the floor. If you were to erase and get rid of that normal force entirely, then the only force remaining would be the force of gravity, and it would follow that force vector. Fortunately, this block is not excessive in size, so the normal force in all of these examples can cancel out with that force of gravity. Another thing that totally gets canceled, and I'll draw it out a slightly different way, this is something that we talked about in class. The rope doesn't recognize that there is a pulley changing its direction. So if you've got little m and you've got big M, and big M is being pulled to the right by that force of gravity, and then you have a force of tension pointing inwards on that rope, and another force of tension coming from the other side, the larger mass, and then you got the other 3 vectors over here that all disappeared. We've already drawn those, the normal, gravitational, and force of friction. What you'll notice is that these forces of tension are also equal and opposite, right? Tension along a rope is going to remain the same at all positions along the rope. That's what the textbook tells us. They give lots of great examples as to why that's the case. And in this particular case, you'll notice those arrows are pointed at one another. So that leaves, essentially, this is the point we wanted to make, only one force unbalanced, only one force not being canceled out. So why is only one force required? The only force, let's write it this way, only force not canceled out is Fg of our smaller mass, of our hanging mass, right? What is the magnitude of that? Well, if you want to calculate the weight of an object, remember, I'm not asking for direction, I'm just asking for magnitude. So this is going to be our smaller mass was 4 kilograms. We have 4 kilograms multiplied by 10 meters per second squared. Again, I'm not including the negative there because they didn't ask for direction. Yes, the arrow is providing a direction. We know that this is a downward 40 Newton force, but they asked just for magnitude. The size of that value, that's what magnitude means, is 40 newtons. At what rate will the whole system, the sliding mass and the hanging mass, accelerate? So here's where we have to get careful. If an object is going to accelerate, it is because a force acted upon it, not just any kind of force. Notice that we diagrammed, 1, 2, 3, 4, 5, 6 different forces up there. Only one was unbalanced. Only one was uncanceled. So the textbook likes to use the Greek letter sigma. And in fact, stats classes, math classes all over the world, they're going to use this letter sigma to represent the sum of, or in our case for physics, the net force, right? The total of all forces acting on the object, was for us, the only one that wasn't canceled is that force of gravity. So our net force, the sum of all forces acting on this object, is 40 newtons. Our mass is going to be the total mass of the entire system. So yes, the hanging block has a mass of 4 kilograms, but the sliding block had a mass of 10. Both of those are moving at the same time. So you're going to get a total mass of 14 kilograms, and they want us to calculate the rate of acceleration. So your rate of acceleration here is going to be 40 divided by 14. A Newton divided by a kilogram is going to give us units of meters per second. So we get 2.86 meters per second squared as the rate of acceleration for the entire system. Right? Again, The weight vector hanging over the edge is the only one that wasn't canceled out. It's the only one that isn't part of a pair. So to apply this in example number 2, right, we're going to use the same half Atwood machine before. Instead, we have a 5 kilogram mass hanging over the edge. It does accelerate at a rate of 0.75 meters per second squared. We want to know the mass of the larger object. We're going to set this up the exact same way, right? Newton's second law states that an unbalanced force, a net force, is responsible for an acceleration. We already know the rate of acceleration, and because we know the mass of the smaller guy, the hanging mass, we also know the weight that is hanging over the edge. So the force of gravity from that hanging mass is going to be 50 newtons. Our mass, remember this was the total mass of the entire system, so this is going to be our mass of our small guy plus, I'm going to label it big M. We don't know what that is, but we do know that that mass term should be the combination of the two of them, and we know that it accelerates at a rate of 0.75 meters per second squared. When we do some fancy algebra here, you're going to divide both sides by 0.75 and then subtract your 5 kilograms from both sides. We're going to get a value for big M of 61.7 kilograms. Please make sure you guys give that a shot, that when you do your calculations, you can get the same values I'm getting. That's what we want out of all of this. So that's your half Atwood machine. Quite honestly, this is going to be the same thing we're going to do in our lab on Monday. For those of you watching this in 2023, when that works out for future years, I'm not entirely sure. But for our F equals MA lab, where you guys are going to provide data and evidence to support Newton's second law, this is the half Atwood apparatus that we're going to be using there. So we'll come back to this. The full Atwood machine is essentially an elevator. I don't know if you ever noticed, but elevators have little counterweights on the back end of them. You yourself in the elevator are technically one of these masses, and then the other mass on the far end is going to be a counterweight. If you would like to go up to a higher floor, M2 gets larger, and they literally add counterweights to that counterweight to make it heavier. You accelerate upwards. And if you would like to go down a floor, then it removes some weights based on how many people are in the elevator cab, and then it lowers you. So what we're going to do first is we are going to draw and diagram let me erase some of those marks I made here. We are going to diagram and represent all of the forces acting on these objects. I'm going to color code these for you guys, so that might be a little bit easier, and then we'll go ahead and derive the equation that we're going to use, very similar to what we did in class. So you're going to have the force of gravity acting on mass number 1, and you're going to have the force of gravity acting on mass number 2. Again, gravity only works in that downward direction, so we have to be very specific about that. And then we're going to go ahead and we're going to draw the tension arrows, because we have tension acting on these as well. So we have the force of tension from mass number 1, and we have the force of tension acting from mass number 2. So I labeled it FT1 and FT2. From here, we're going to rewrite the exact same equation we were working on before, right? The equation that we started all of this was Newton's second law. The sum of all forces acting on an object provides that rate of acceleration, right? I'm going to take this and I'm going to rearrange it slightly, though. And I'm going to rearrange it to write A equals, make that sigma look more like a sigma, our net force divided by not just any mass, right? I'm not going to pick 100 and I'm not going to arbitrarily pick 200. We have the mass of the whole system that's moving. So very similar to 5 plus m or 10 plus 4 in the last two examples, respectively. We're going to have the total mass here, and so this should be 300 grams that we're dividing by towards the end. Of course, you have to convert that to kilograms, so it should be 0.3, but we'll get there when we get there. For now, I'm going to write out all of the different forces, then we'll talk about direction and assigning positives and negatives here. So first thing I'm going to write out is going to be blue. We've got 3 different forces. Our first force is the force of gravity from mass number 1. We are then going to add that to the force of tension from mass number 1. We're going to add that to the force of tension from mass number 2. And we're going to add that to the force of gravity, or the weight of mass number 2. All again divided by our total mass, which you could start labeling if you wanted to as M1 plus M2. Technically, that's not incorrect, right? We would just add them together when we finally get there. Now, in a different color, let me pick a different one. Green, fabulous. In a different color, I'm going to go through and I'm going to assign positives and negatives. Now, when we put these masses in, M1 is going to be 0.1 kilograms and M2 is going to be 0.2 kilograms, right? We need to actually convert those into kilograms because that's our standard unit of mass. So if we have a larger mass sitting in a position above, really it doesn't matter. If we have a larger mass for M2 than we have for M1, the whole system is going to accelerate. M1 is going to be traveling upwards, up and over that bend, and this pulley that we have up here is going to be rotating in a clockwise direction. And M2 is going to be falling. M1 will be rising, M2 will be falling if M2 is larger. So we're going to describe that because that's the direction the system is moving based on the two masses. We're going to describe that as positive. And what I'm going to do with that positive value is I'm now going to go through and label all of my forces, all four of them, with positives and negatives based on who is pointed in the same direction the whole system is accelerating. So FG1 is pointed the opposite direction the system is accelerating, right? Because this arrow down here would be pointed up and over, up and over. So this, because it's pointed in the opposite direction, is going to get a negative. We have negative FG1. FT1 is pointed in the same direction, so that's going to be a positive. FT2 is pointed in the opposite direction, so that's going to be a negative, and FG2 is pointed in that direction. The whole system is accelerating, so we're going to label that as a positive. From there, what I want you to recognize is, again, from our textbook, we should realize that tension along a string is always going to be the same. So really, what happens here is this whole thing is going to get a lot easier because that completely disappears. Whatever that value for tension is, I suppose we could calculate it if we knew the rate of acceleration. But whatever that force of tension acting on this system is, it's going to be equal across the entire rope connecting these two masses, and because those vectors are pointed in opposite directions, they completely cancel. We cannot do that with FG1 and FG2 because FG1 was made up of 0.1 kilograms, FG2 is 0.2 kilograms. Those are going to have different weights. They will not cancel. They will reduce because one is positive and one is negative. The total value will get smaller, but really what you're left with is negative FG1 plus FG2 all divided by M1 plus M2. I don't know why I made that M1 and I. There we go. M1 plus M2. So when we go to do this calculation, we have a rate of acceleration. I'll cut this off right here. There we go. We'll have a rate of acceleration that is equal to negative 1 Newton, because that's going to be 0.1 kilograms multiplied by 10 meters per second. That's how we calculate a weight, plus 2 newtons. And again, this is going to be a positive 2 newtons, all divided by 0.3 kilograms. And that's going to give us a value of 3.33 meters per second squared. Now, once we have that value, we can go back and we can actually calculate what that value of tension should have been inside this Atwood machine. And to do that, really, you only need to look at one of the two masses. It doesn't matter which mass you look at. Let's look at M1, just because it was the smaller of the two masses. But we can use the information we know about M1 in order to calculate what that force of tension would be. Again, objects only accelerate because there's a net force acting on them. We now know the rate of acceleration is 3.3 meters per second squared. We know the mass of M1 is 0.1 kilograms, and we can then use the sum of all the forces acting on it in order to calculate what that would be. Because all the forces acting on just mass number 1 was a force of gravity plus a force of tension. That was equal to M1 multiplied by A. And you can, if you wanted to, move some stuff around, move some stuff over. Let's see, in this case, we want to take into account those vectors. Remember, your FG1 was a negative value because it's pointed in that downward direction, so we include the negative here. FT1 was in the same direction the system was accelerating, so that can be positive. The way I would take this, I'll move it down here, and rearrange this particular equation, because I like rearranging stuff before I do the math, is ft1 is equal to m1a plus, because we have to add that weight vector. In order to calculate weight, it's always m1 multiplied by g. So then ft1 is equal to, what is that, 0.1 kilogram multiplied by 3.3, and then its weight was 1 Newton, right? 0.1 kilogram multiplied by 10 meters per second squared. The force of tension acting on this rope is 1.33 newtons. If we put a force probe somewhere along that rope, somewhere along that string, 1.33 newtons would be the force of tension that it measures inside this particular system. All right, that's really, it seems like a lot, but that was because that was the first time I went over it. So let's jump into problem number 4, really, which is the exact same scenario. It's the exact same idea. M1 represents an elevator car full of people on the first floor, which have a mass of 950. So I'm going to start labeling these. We have 950 kilograms for M1. We have a counterweight, which is M2, of 1,500 kilograms. How much tension? All right, well, in order to get tension, we have to approach this the same way. We needed to know what that rate of acceleration for the whole system is, so we can go ahead and calculate that rate of acceleration for the whole system. Remember, it's negative fg1 plus fg2 all over m1 plus m2. Make sure you include those negatives. We plug everything in. We should get a rate of acceleration of 2.24 meters per second squared. Then we can come back and plug it back into the same equation we used over here. I like always going back to the first mass. Even if I ask you what is the force of tension as it's connected to the second mass, the tension along the rope is going to be the same. So it really doesn't matter which one of these we look at, which is why I like to always stick with the same one. That way I know, oops, I was clicking something else. That way I know I don't get tripped up, I guess is essentially what I'm saying. It doesn't need to be a new unique problem every single time. If you're asking for the tension, either tension with respect to mass 2 or tension with respect to mass 1, they're going to be the same values. So again, M1 was just 950. Make sure we're using that one twice. G is 10, A is 2.24, and we should get a force of tension. Now, mind you, this is an elevator with actual people inside of it, which is why this number is so much larger. We get 11,628 newtons. It's a lot of tension. It's a lot of force. But those are your Atwood problems. Assignment number 2, what you guys should be working on. Again, if this is 2023, you guys will be working on this tomorrow with a sub, which is why I wanted to make this video. But feel free to use this either as a review for the test. Maybe you missed the day where we went over it in class with the notes. Maybe you just want to hear my lovely voice as you go over and attempt assignment number 2 on your own tomorrow because you're a brave soul, but you like the guidance. That's perfectly fine as well. That's really about it. Please don't ever hesitate to reach out, ask questions in class, or shoot me messages on Teams, email, whatever. That's really it. Let me know if you guys have questions or concerns. Take care, guys.